Okay, thank you for that introduction, and thank you for the opportunity to be here and speak to you today. So I'm going to talk about the topic of recent research, or I guess past 5 years, and I'm going to really introduce it in a tutorial way with going through the background and really objectives of doing research in power electronics in general. But then we'll get to the actual research topic and some of the thinking behind it and some results. So for most of my career, one of the things I've been very interested in is really converter circuits and topologies. I think there's been a lot of work through the years in this area, and it's pretty well understood. And yet, the power electronics field continues to explode, and we continue to have new applications where we need new circuits. So the interesting thing today is that we have these silicon carbide devices that can switch very fast at much higher voltages and power levels than we've been able to do in the past. And this really opens opportunities for new applications at much higher voltage and power levels. So one way to build a larger, say a higher power, higher voltage converter, say a bigger boost converter, is to buy a bigger, two big transistors and a bigger inductor and some bigger capacitors and connect them in the old way. And that's probably the normal way to do it. But the problem is that those transistors are built in modules, and in fact, the module of the big transistor is a lot of small transistors connected together inside the module. So it's a brute force approach, and in fact, I guess I'm going to present today that you can take those devices and connect them with better circuit topology and get not just an incremental improvement, but a really significant transformational improvement in the converter performance. So we have an example of really a modular version of a boost converter, or it's the boost function in a much different converter topology, where we can reduce the losses by a factor of 4. So this is something that's worth doing. Okay, now a lot of people don't like the complexity and say this is too complex, or they say there's too many parts and so it's not as reliable. And so I've done a lot of work to try to understand exactly what they're saying and how to systematically and scientifically show they're wrong and that this is worth doing. So I want to talk about that. So to start out at the very beginning in a tutorial nature, just research directions in power electronics. Frankly, this is true about any research in any engineering field, but first of all, the research needs to support or develop a technology. We need to think about what is the application, and if we succeed, is this worth doing? Is it going to matter? So do we have a good product that this research could support, or that could develop into a good future product so that it's worth doing? We have a lot of emerging applications. Some of the recent ones that there's been lots of research on are, electric vehicles or other kinds of electrified transportation, charging of batteries or electric vehicles or electronic devices, microgrids, which really is a power system problem, but it needs power electronics, and there's many more. So electrified transportation, solar power electronics, and microgrids are what I'm interested in currently. So power electronic research that advances power electronics in new applications is certainly a fruitful direction to look. And then in parallel with that, research that improves performance metrics of our power electronics technology, which has always, from the very start, been about power density, efficiency, and I'm going to talk about this quantity Q in a minute, but it's equivalent to efficiency, the reliability, and the cost. So always we want research to improve these metrics. These are our equivalent of Moore's law. They're not Moore's law, but they are the thing that we are trying to advance. And then I'd say modeling and control for me has always been a very interesting topic, and it was very important to do. I mean, there's a lot of opportunity to do research in this area. When I was a student or a young professional, and one could get research contracts to work in that area, but today it's pretty hard to get a research contract where the object is simply modeling and control. Yet it's important to build converters, and so we need to teach our students these things. But to incorporate or to do research on this topic, it needs to be research that furthers the things above it. So it furthers the performance metrics or furthers an application. So the things we have in power electronics that we're advancing, we have improvements in the components, and the big thing here has been wide bandgap semiconductors in the recent years. Advances in magnetics and capacitive elements are also important, but they don't advance very fast, while what really pushes the technology has been the semiconductors and continues to be. In parallel with that, we have improvements in converter circuits and topologies, we have improvements in control, and we have improvements in the mechanical side, the packaging and interconnects and thermal management. Now, an improvement in any one area is a good thing, but if you want to actually improve the power electronics technology, you need to incorporate all of them, and you need to understand all of them and make decisions about research that incorporate all of these. So, for example, we can take the new wide bandgap semiconductor device, plug it into the old circuit that we already know, and get an incremental improvement in performance. But if you take that new device and make improvements in the power converter circuits to go with it, and in these other things, you can make a much more significant improvement. And so an advance in one area gives us opportunities to make advances in the other areas as well. And to make the most significant advance in overall power electronics technology, we need to do all of these at the same time. This is a slide that I made recently, but it could have been made in 1970 or the 1970s, which is this power density versus reliability. I have to say, when I was a student in the 1970s, people were trying to improve cost and loss and size and power density then. And I think people understood that you could push on one of these things, and then the other two would degrade. And what happened, the story that happened was that in the United States, the Department of Defense would request higher density power converters for things like ships and airplanes. And what happened was that the power supplies they procured were unreliable. And it got to the point that there was a committee formed, headed by this Commander Willoughby of the Navy, to study these problems and do something about it. And so there's this famous Willoughby report that came out in 1982 that told people how to design power supplies, but what it basically said was that you can't advance this technology without some fundamental advances that are made. You can't just push on size and put your converter into a smaller box that runs hotter and fails faster. So we require fundamental advances in the technology of converters in order to achieve the goals of higher power density and these other things. that are desired. And this, in a nutshell, is the whole technology of power electronics, and it's what we're still doing today. So we can think of a space that is some combination of cost and loss and size and reliability. And if we can make that space better and better, then we're advancing the technology, and we have. And I was afraid of this. Okay, those are ADAs, that's efficiency. One thing that we've done in the field is learn how to build much more efficient converters. And so maybe back in the 1970s, a 75% efficient converter was a great thing. Nowadays, it's a crummy converter, and we're building converters with efficiencies in the mid and high 90% range. And its efficiency has always been recognized as being paramount, and the reason is that we're putting our converters in boxes that are loss limited. You have a cooling system in your box. It can only extract a certain amount of energy or heat out of that box, and so we're loss limited. There's been a question, certainly in the places like ARPA-E and DOE circles, of how do we make transformational and not incremental improvements in our technology. And if we simply say we're improving our efficiency by 1%, that sounds incremental. And so we've adopted really a new measure of this performance that we call Q, and it's the ratio of output power of our converter to the loss. And basically, we want to build a small box with huge input power and huge output power. The smaller the box is, the less cooling it has, and the less loss it can handle. So if we have a box that's a certain size with a certain cooling performance, then the loss is a given number. And if we want higher power density, we need to make higher output power with the same loss. And so Q is the direct measure of that. So this is efficiency over 1 minus efficiency, and there's a plot of Q versus efficiency, and as you go to 100% efficiency, Q goes to infinity. Okay, this is in fact the real measure of technology, of power electronics technology. So we have a certain box size, P loss is fixed. If we can double Q, we can get twice the output power and twice the power density. And if you go from 98% to 99%, you've doubled your power density and doubled your output power. So we now have DOE agencies that are saying we want a box with a higher Q, and we want to double Q, and that's a non-incremental improvement, even if it means a 1% improvement in efficiency. Okay, silicon carbide devices are very interesting to me right now because they represent a pushing forward of the limits of power electronics applications to much higher voltages, much higher currents, while moving to higher power density. So really, these devices are replacing silicon IGBTs, but they have much faster switching, so we can run them at hundreds of kilohertz instead of 10 kilohertz. And we can extend high-frequency power electronics to much higher voltage and power levels. But they're more expensive than silicon. And so if you just replace your silicon devices with silicon carbide devices, you'll get, since they're faster, you'll get lower switching loss. The other losses might not change, and you get a much more expensive device. So the opportunity here is to redesign the whole approach. So we use the newer devices, but then we need new circuits, we need new control, and we need new packaging to realize non-incremental improvements in our converter performance. Okay, and new applications then become open, and what we're seeing is a lot of papers and research in the area of converter architectures that usually are highly modularized. So multi-level modular converters and so on at these higher power levels. I guess two examples of opportunities here. In the transportation business, power density is critical of what fits on the vehicle, and so we need high power density at these higher power levels. String inverters for solar systems, solar PV generation, are another case where high power density is needed, and so this is an opportunity as well to pursue this. Okay, in the area of converter topologies then, we see, I guess we see a lot of papers about modularized systems. So they're much more complex than the simple converters we built in the past. And the two simple examples, just very rudimentary examples of what we can do, the multi-phase conversion is very well known and highly applied, where we take converters and put them in parallel and operate the switching out of phase to cancel current harmonics and reduce the capacitor currents. And so we can get substantially reduced input and output voltage and current ripples. And effectively, we're using the same semiconductor area more effectively and reducing the size of the capacitive filters. But this takes more complex control. We have more gates to control, more gate drivers, and so on. The other direction is the multi-level conversion, and here's a very rudimentary, well-known version of that, where we put devices in series. The switches are exposed then to half the voltage stress. The inductor has less applied voltage, and so it can be greatly reduced in size. It's a more complicated circuit. It requires more complicated interconnects and control. And it adds a capacitor that actually is a pretty large capacitor. That is an issue with that. So we have many multi-level topologies that are doing this multi-level switching, and we have highly modularized systems. You could think of this as two modules in parallel in the literature, and we get better performance where we can have more complicated switching that reduces the inductors and capacitors and can lead to higher higher power density. One of the big complaints about this, though, is that you count the number of devices and there's more, and so it's less reliable. More devices means a higher failure rate. You have more transistors, you have more gate drivers. So I guess I want to take that statement on here and argue that better performance can mean higher reliability, not lower. And these are fundamentally better approaches that improve the performance of the converter. If they reduce the loss, you can reduce the temperature rise and you can get higher reliability. So some research objectives of projects that I and my colleagues have done recently at Colorado is really looking at how to build more complex or modularized converter architectures that push the technology metrics in a significant way. And so we can measure the technology really by this combination of loss or Q, as well as cost and power density. And the claim is that even though it's more complex, it's worth doing it because we get these performance benefits, and that even though it looks like on the schematic there's more parts, we improve the reliability. Here's a result, an experimental result. This is the boost converter. That's the specifications of the boost converter that's in the powertrain of the Prius that boosts the battery voltage to a higher voltage to drive the inverter in the main powertrain of the Prius. And this is a conventional, just simple boost converter efficiency curve that is in the Prius. And here is what we were able to achieve, where we improve the efficiency and we actually maintain this very high efficiency around 98%, all the way from 30 kilowatts, that's the rated power, down to 1 kilowatt, and then the efficiency drops off. So this is more than just incremental. It's cutting the loss in half at full power and by a lot more than that at low power. And when you're able to get that kind of performance benefit, then the Q is much higher and temperature rise is much lower. So we achieve this really with new converter circuit architectures, control, and interconnects. We're doing it now with wide bandgap devices. I think we've developed a new family of composite converter architectures. This is a composite converter. What's meant by that is it's a modularized converter system where the modules are different. They're not all the same. Okay, and so we're working on this now in a 100 kilowatt electric vehicle application in the main drivetrain that does both conversion of the main powertrain power as well as using some of these composite converter modules to integrate charging. And we're developing planar magnetics for these kind of power levels so we can run our devices in the hundreds of kilohertz range. Oops. Okay, so how do you connect converter modules together to do this? You can't just throw modules up and interconnect them in a random way. In fact, most ways of interconnecting modules don't work very well. So to make it work, you have to really look at the fundamental conversion process that the converter is performing and do that process in the most efficient way. And so here's some more theory from the distant past. Direct and indirect power in converters. So here's a buck converter where we have an input voltage, we're stepping down the voltage. In the process, we're increasing the output current. The buck converter has current gain, and the switching process is converting some of the input power into AC at the switching frequency, and then rectifying it back to DC to recover it and operate with near 100% efficiency. So there was an MIT thesis in 1969 that described all of this, and it identified the direct power flow and the indirect power flow. So the direct power is the power that does not go through an intermediate conversion to AC and back to DC, but it simply flows to the output. So if you just leave the transistor on, connect the input to the output directly, then you just have DC flow of power to the output, and that's called the direct power. Indirect power is what you get when you switch the transistor with some duty cycle and switching frequency. And in that case, there is some average voltage across the transistor and some average current through the transistor. When you multiply those, you see that it appears that the transistor consumes DC power, the product of the average voltage and current, and it generates AC power at the switching frequency that is equal to the DC power it's consuming. Here's a little mathematical proof of that, which I'm not going to go through. So the transistor is acting like an inverter to produce AC power. Some of that power is temporarily stored in the inductor, and then it gets rectified by the diode. And the diode rectifies the indirect power back to DC, and it supplies some additional current that adds to the DC component of transistor current that produces the gain and produces additional output current. So this process of indirect power flow has a lot higher loss than direct power. If you just turn the transistor on and connect the input to the output so the converter doesn't do anything, you have very low loss. That's only the conduction loss of the transistor and the DC resistance of the inductor winding generating loss. But when we have this switching and we have this indirect power path in the converter, then we have switching losses in the devices and we have AC losses in the magnetics core and especially the AC copper loss, leading to significant loss. And the indirect power mechanism then is the one that is the biggest problem in reducing our efficiency. So how can we do the required function of indirect power conversion to get the gain, the voltage or the current gain that we want in our converter in the most efficient way? So we looked at a lot of ways to do it, and the best way we could find was this dual active bridge circuit. And you can invent other ways to do it, but this one actually is pretty remarkable. When you operate the dual active bridge with a fixed voltage ratio that's equal to the turns ratio, then the efficiency is very high. Under these conditions, it has trapezoidal current waveforms through the transformer winding. The tank inductance is tuned to optimize the efficiency. The switches are operated with 50% duty cycles, and there's some phase shift between the primary and secondary side switches to maintain this fixed voltage ratio. And in this case, we found we can build isolated converters with a fixed voltage ratio with efficiencies of maybe 98.5%. Also an interesting thing about this circuit, the currents in the capacitors are very low. To the extent you have trapezoidal currents, you have very little ripple in the capacitors. It has zero voltage switching of all the devices, and so it has low switching loss. We have to put some work into designing good magnetics with the low AC proximity loss, but then we can build a good, very good converter of indirect power. So here's a plot of the AC loss from the indirect power and the DC loss in a boost converter as you increase the duty cycle. So at duty cycle of 0, the boost converter just connects its input to its output. There's no AC loss. There's just the conduction loss, and we get very high efficiency. And when you operate the boost converter near that point, which we call the pass-through mode, the efficiency is very high. As you increase the duty cycle and make the boost converter do more work, which really is increasing the indirect power in the boost converter, then the AC loss goes up quickly. So what we want to do is not use things like boost converters to do the indirect power conversion, and instead use a DC transformer circuit to do indirect power conversion as efficiently as possible. And then we put boost or buck modules around the DC transformer in order to control the voltage. And that's okay as long as we run these buck and boost converters near their pass-through modes where their efficiency is high. Okay, so with this strategy, I'm going to demonstrate we can get, first of all, an order of magnitude reduction in the RMS currents of the capacitors, which makes them much smaller. And really, the capacitor filtering is filtering the indirect power, the AC currents. So if we minimize those, we can minimize the capacitor size. We can also reduce the magnetics requirements because they don't have to store as much of the indirect power. And we get high efficiency over a wide range of operating points because we're mostly the DC loss. So here is an example. This is a boosted electric vehicle powertrain architecture. We worked with Toyota on a lot of these, and this is really the architecture that is based on the Prius system. And in the original Prius, they have an IGBT boost DC-DC converter that takes the battery voltage and steps it up by a factor of maybe 3, and then that drives the two inverters actually in the hybrid system and AC motors. So in the conventional boost in the Prius, these IGBTs are in a semiconductor module, and there's actually multiple die connected in parallel inside the module, depending on the power rating of the electronic system. They switch typically at 10 kilohertz or so. When they have to boost by a factor of 3, the efficiency suffers, and there's also poor partial power efficiency. The current in this capacitor is very large. The film capacitors in the Prius are maybe a third of the whole electronics module, and the efficiency of the boost converter dominates the electronics, the efficiency of the electronics. So a composite architecture that we used was this. There is a boost converter between the battery input and the DC bus output, but the boost converter operates over a very limited range at low duty cycle where the indirect power is low. Then we have a DC transformer that does most of the conversion of the indirect power at very high efficiency. So in the boost converter, the indirect power is giving us gain, voltage gain, and we're getting that now from the DC transformer that has higher efficiency. We also find we need a buck converter that operates near its pass-through mode to be able to control the output voltage smoothly. So there's 3 boxes here. Each converter is a partial power module, and you can think of this as taking a couple of the die that are in parallel in this module and using them, say, for this converter, a couple more for this converter, and so on. And to be fair, in comparing these, we want to use the same amount of semiconductor area here as we have there. So there's actually we have different versions. This is a buck with MOSFETs, a boost with MOSFETs, and then this DC transformer from the previous slide. Here's an example of how this works. We have, say, a 200 volt input and a 600 volt output. We design the DC transformer with a turns ratio of 2. At this operating point, you can run both the buck and the boost in pass-through modes, where they simply connect their inputs to their outputs and don't switch. So they have super high efficiency. The DC transformer is providing the voltage gain. It's taking the 200 volts from the battery and making 400 volts that we stack on top of the boost 200 to get 600 total. This is so we can optimize this converter circuit to work at a key operating point. Here it's 600 volts and get very high efficiency. So if we have a 98.5% DC transformer, and then these buck and boost just have some relatively small conduction loss, we can get a system efficiency that's above 98% for this example. If you want to raise the voltage more, you increase the duty cycle of the boost to boost its output voltage some. If you want to lower the voltage from this point, you can lower the duty cycle of the buck to reduce the voltage here. And so we can do switching that is still at very high efficiency with low indirect power to control the voltage. There's all kinds of ways to build composite architectures, doing different things, bucks and boosts and other buck boost applications. So there's a lot of possibilities of things, similar approaches. Current project, then we have a 200 to 400 volt battery input. We have 100 kilowatts rated power. We want to produce a DC bus voltage of 975 volts and 1200 volt maximum. We want to achieve a power density of this whole boosted system, including its filtering and inductors and capacitors, of 22 kilowatts per liter. And then this CAFE weighted Q I'll talk about in a minute, but we want a high number for that. Okay, mean time to failure. So we have all these converter modules and devices and gate drivers. How can we get up and claim that there's a benefit in in efficiency and in mean time to failure? So to talk about mean time to failure, we need to model how the device is used over its lifetime. And to do that, we go to these industry standard, for the automotive industry, standard drive cycles. So each country has a series of them. In the United States, the Environmental Protection Agency has these different drive cycles, city driving, highway driving, and so on. And they actually have a model, the corporate average fuel economy model, to compare cars and their gas efficiency. But we take that then as a model of how the average car is used over its lifetime. And so here's one of these. This is actually this US06 aggressive driving schedule. So this is the speed of the car in over a 10-minute cycle. And with a model of the car and model of our converter losses, we can work out what the losses and the power will be over this drive cycle. And here they are for our composite system. So with this, we can model what the losses, the average loss will be over the lifetime of the car, predict the average temperature rise, and then use that to predict the mean time to failure. There's a lot of work to do this, and it's really, after all these years, it's still very hard to have good losses of the AC, or good models of the AC losses, such as proximity and switching loss. And so we take theoretical models and then we calibrate them with laboratory prototypes to get really a semi-empirical model of the switching loss and the proximity loss. Here's a plot for different bus voltages and different output powers. The different colors are efficiencies. So 99% efficiency is dark red, 95 is almost white. And then over this space of power and voltage, which is like acceleration versus speed of the car, we have plots then of the efficiency, and then these blue lines are the trajectory in the space of what happens over the US06 drive cycle. So we go all over the place, but you can see that we spend a lot of time here and we spend a lot of time there. So if you want to make a difference, then improve the efficiency here and here. So what we can do is optimize the design parameters of our converter to try to maximize the efficiency, or the average efficiency, over the drive cycles that model how the car will be used in its over its lifetime. So again, here is the efficiency curve, and this the dots here are measured efficiencies for this composite. It was an early silicon composite converter. This is at just a fixed input voltage and output voltage, and we're varying the power. So this one I think is at 650 volts, and then we're plotting what it does here versus power. So when you play out the drive cycle like this over this efficiency curve, then we find the average loss and the average output power over this curve, over this trajectory. For the conventional curve like that, we get this Q, or average output power over average loss of 17.9, and with a composite approach and that kind of efficiency curve, we improve that by a factor of, what, 3 to 4, to 51.6. This is with essentially the same magnetics volume, just a different topology. So the average efficiency over the drive cycle goes from a little under 95% to a little over 98%. Here's 4 different approaches. The silicon IGBT, again with a just under 95% efficiency. The silicon MOSFET composite converter, which was just over 98%. This one is what happens if you just brute force put silicon carbide MOSFETs in place of the IGBTs in otherwise the same circuit. It's got some benefit. You increase the efficiency to 96, so a little bit. You increase this weighted Q a little bit. That makes the average temperature go down. We're assuming the same cooling system with the same thermal resistance here. And then if you calculate the mean time to failure, these calculated formulas are well known to have a lot of assumptions and not be very accurate. But to be accurate, we take the same formula and apply them in all cases. So we're at least trying to compare on the same basis. So the silicon MOSFET composite approach has maybe a ×3 improvement in mean time to failure, even though you may count more devices. The silicon carbide MOSFET in the brute force replacement does even better on this standpoint, because the silicon carbide devices need smaller gate drivers. There's smaller capacitance for the same power, and that has some significant benefit. And then if you put silicon carbide in the composite approach, we get a little bit better efficiency and better weighted Q, and we're getting significantly higher mean time to failure. It's really a combination of the best efforts of these two things. So you don't just count MOSFETs. If we compare things on a really systematic basis, here the fact that we have a higher component count is outweighed by the fact that the temperature rise is much lower because we have much higher efficiency and higher Q, and that leads to much higher mean time to failure. This is the same data. I think what I would add here, we're running our silicon carbide converters at 100 kilohertz at 240 kilohertz. At 100 kilowatts at 240 kilohertz. Our film capacitor size is reduced by a factor of almost 10, and our core volume with this high frequency is reduced as well. Controlling the converter, these things are more complicated, and so there are more control problems. Here's a plot of closed loop control of this composite converter. What's shown here is we have a stair-step voltage reference, so we're commanding the output voltage to step from just under 300 volts up to almost 800 volts, then back down, and this is the actual response to that of the output voltage taking these steps. Below this are the duty cycles, or the gate drive signals. So this is the buck drive, the boost drive, and the DC transformer drive. So we go from the buck turned off, the boost switching, and the DCX turned off. Through here, the buck has a duty cycle and is pulse width modulating. The boost is in pass-through mode with these voltages, and the DC transformer is operating. And then here at high voltage, the buck is in pass-through mode, we're boosting, and we have the DC transformer running. So it's possible to control these. It's more complicated, and hire a good PhD student to work out the control. There's some interesting problems to solve, but they can be controlled. We're currently working on decentralized control, so we have local controllers of each module to try to make it easier to control and easier to expand the system to more modules without having to start over and redesign a central controller. And there's issues like passive damping of converters in pass-through mode and negative resistance oscillations. Planar magnetics is another interesting project here. So we're working on building high-density planar magnetics at these higher voltage and power levels. So this is a pretty big transformer for DC, or planar magnetics transformer for the DC transformer module. There's a US quarter for comparison. Even though we reduce the loss and have higher efficiency, we're also greatly reducing the power level relative to where planar magnetics is usually used. And so there's just a lot of loss inside the planar magnetics, and so we have to integrate this work with cooling. And so how do you get the heat that is generated in the inner traces of the printed circuit board winding of the planar magnetics out? And we have to mount this on a cold plate inside the vehicle that receives cooling from the radiator loop. We need thermal vias and modeling of the losses inside the printed circuit board, and really co-design of both the thermal and electrical characteristics to build planar magnetics that work at these power levels. But it can be done, and it does let us further increase the power density of the system. So we share the cold plate between the semiconductor modules and the magnetics modules. Okay, so in conclusion, I claim highly modularized converter systems lead to fundamentally better performance, and really, they provide a path to high power density at new levels of voltage and current in our switching converters, and I think are a good way to go for 100 kilowatts and above. We can get improvements in the system efficiency, or Q, that lead to significant reductions in operating temperatures, and those then greatly improve our reliability. So the systems we've looked at, these composite converter systems, use partial power, buck, boost, and DC transformer modules, perhaps other modules. The modules, the buck and the boost, the switching converter modules, we try to operate near pass-through mode where they have very little indirect power and therefore have very low loss and have low capacitor currents. So I would claim that we can extend high-density, high-frequency power conversion to much higher voltage and power levels with such modular approaches, and it's an interesting problem then to look at higher power applications that benefit from high power density, such as electrified transportation and photovoltaic string inverters. Okay, thank you for your attention.
Thank you very much for a very interesting presentation.
Are there any questions?
From the audience? Yes, please.
Should he come up here, or?
Come here.
Yeah. Does it? It doesn't work?
Yeah, so for, is this working fine? Yeah, so for this,
One.
Yes.
Okay.
Thank you.
for the same study, I was just wondering where this GaN stands, I mean, in terms of converter reliability specifically, and converter control, I mean.
So we did not use GaN because it's a automotive application. We actually did this project, and we currently are doing a project in connection with Toyota. And their interest is in silicon carbide, but I think in automotive in general, the current emphasis is silicon carbide. And there are GaN in the automotive applications. I guess there's been some skepticism about it, although that could change. So reliability of GaN really isn't something we looked at. It wasn't considered. I think you could build GaN integrated circuits that are composite architectures that would be interesting to do. But, okay.
Are you satisfied with the answer?
Yeah.
Okay.
Do you have more questions?
I can ask a question if you want.
Please introduce.
Thank you, Kamal Al-Haddad from ETS Montreal. I like the idea of having the 3 boxes to deliver the same output power. But how did you come to optimize that the boost converter that is working at zero duty cycle? So it's a pre-regulated almost, the 3 bucks, like for example here. So you have the D0 here for delivering 10 kilowatt with 50 watt. I never worked with boost with D equal 0, but you must have D equal epsilon to throw the power. But how did you optimize that you pushing in the buck converter 20 kilowatt and in the boost 10 kilowatt? How did you come to this?
These are good questions. This is just one
The
voltage.
boost is really working as a pre-regulator, as a regulator, adjusting the 200 volt. It depends on the output voltage, if the level is high or no, basically.
Right, so if we want more than 600, we
Yeah.
start raising it here. Yeah, and we increase the duty
So
cycle.
why 10 kilowatt, not 15 kilowatt or you have?
So how the power splits depends on the turns ratio here.
This one here is a DC to DC converter at a fixed.
So it's a fixed ratio, but we can choose its ratio. So you could say make this one in as 1.5.
Okay.
And so then we would have 300 volts here, and the boost would have to switch and make 300 volts to get the 600. So that is optimizing the system to have the boost be in pass-through mode at a lower voltage. So one of the things we do is choose that turns ratio so that when you go through this, all these trajectories, you have the highest efficiency at the places where you spend the most amount of time over the lifetime of the car. So it's a design variable that we can use for optimization. It's one of the design variables. And I'll say we also look, there are a lot of other ways to take converter boxes and connect them. We looked at a lot of them, and this one gave the best results of the ones we looked at for the application that we had.
So the fine tuning of the output voltage is assumed by the buck or by the boost? By the boost.
By both.
By both.
So
The idea of D equal 1 and D equal 0 is really
Interesting.
amazing.
yeah. So yeah, what we want is we don't want D to get too far away from pass-through mode. But we're not afraid to let it be close. But so this converter can work down to output of 200 with 200 in. You make boost and pass through, and the DCX you have to turn off and short its output devices. So it's just a shorted output. And then to go up from there, you start switching the boost, and then at some point you start switching the DCX. And when you turn this on, you turn the boost off. And so there's a lot of mode switching, but the controller does that.
Very interesting.
Yeah.
Okay.
The DCX is a planar transformer, is it?
Yes.
Yes.
So all of the magnetics are planar in our prototype. Yeah.
So, and if I got understood your presentation, the Q is in modularity of these converters, yes? You can, let's say, optimize the book module, you can optimize the BOST model, and you can optimize the DCX model, depends on the application. Is that true?
Right. So the turns ratio is the biggest thing, biggest choice to optimize, but the values of the inductances affect when these converters have zero voltage switching and not, and how big the ripples are. Those are things that can be optimized also. And
So-
at some point, we write an optimization program that takes these models and goes through this and runs overnight and optimizes. However, it's not just throw it on the computer. The real thinking behind it is find the places where you operate the most often, get your converters to run in pass-through mode, or be in the best points where you operate most often.
From the
He is using 400 watt to push 20 kilowatt, whereas he's only using 50 kilowatt, 50 watt for 10 kilowatt. So his long path is not optimized. You have 400 watt losses.
Right.
The two boxes for 20 kilowatt, whereas on the boost type you have only 50 watt losses.
this is 50 volts, 100 volts.
No, 8 times.
Yeah.
These two boxes.
So this is my feeling is the idea is to use the benefits of the transformer, the planar transformer, to adjust the output voltage level to optimize the switching losses in the converters.
Right. The interesting thing is how I think of transformer isolated converters as being low efficiency. How is it that the very best way we can convert indirect power is with a transformer isolated converter? And I think that the answer is that these switching converters are much worse if they have a wide conversion ratio, whereas the transformer isolated version wins then. But it only works under these one certain set of conditions where we can tune it very well.
Are you satisfied
Okay.
with this?